This module is dedicated to binary search trees and in particular yung mga balanced binary search trees. We encountered this particular type of data structure when we introduced yung transform and conquer in module 4, yun yung AVL. But for this module, we will discuss more types of balanced binary search trees such as yung red-black trees and B trees. Okay, so before we introduce those, let's start with a short review of binary search trees, or commonly abbreviated as a BST. Okay, so a binary search tree is a binary tree, meaning every node can have at most two children. It also has a root, so hierarchy is important in binary search trees. So may concept tayo ng parent and children. And it is ordered, so we need to distinguish that there's a left child or a right child. Okay? So aside from the properties that we can get from a binary tree definition, yung binary search tree has some additional properties. And yung first property is that um, each node in the BST stores a key. So most of the time, we refer to the nodes using their key, and they can also have some auxiliary information like data or value associated to the key, because this is important in implementation of a dictionary. So we try to search for a particular key and then access later yung actual or corresponding value of the key. So we can use this for storing and retrieving contents of a dictionary. The second property is that every node in a BST is strictly greater than all keys to its left and strictly smaller than all keys to its right. So, for example, if we look at 9, all nodes na nandun sa left subtree are smaller than 9, strictly smaller than 9, so walang 9 na nag-exist, and all nodes greater than 9 ay nasa right subtree. And that is true to all nodes in the tree. So, if we look at a particular subtree na ito, for example, itong part na to, 2 is less than 3, 4 is greater than 3. Let's recall one important property of a binary tree, which is the height. The height is the length of the longest path from root to a leaf. So, for instance, this graph has a height of 4 because the total number of edges, which is equivalent to the definition of a path, is equal to 4. So, we have 1, 2, 3, 4. And because of that definition, a tree with a single node has a height of 0 kasi wala namang edge. And by convention, if we have an empty tree, so wala siyang nodes, the height is equal to -1. So binary search trees are important for maintaining a sorted list of keys. Uh, and if we have a binary search tree, if we traverse the keys in an in-order manner, so kapag in-order kasi 'di ba, left, root, and then right. So if we try to traverse this tree and enumerate all the keys using the in-order traversal, ang output nun is a sorted list of keys in an increasing order. So it's important for maintaining a priority queue, for example. Maintain a list of sorted elements, basically. So we use the binary search tree. Okay, so just like any abstract data structure, we need to define several operations that we can use. So one important operation is the search operation. In a regular array implementation, we can perform search by linearly checking all the elements in the array, but we know that by sorting the list of elements, hindi mo kailangang laging magkaroon ng linear in the worst case. But pwedeng mas mabilis yung search if we have a pre-sorted input. So one way of maintaining that sorted list is by keeping it in ABST. We can search for a particular element in a binary search tree by utilizing the property of a binary search tree na everything here sa left is less everything sa right ay more. So, yung search operation is traversing the tree from the root to a particular leaf, and we can traverse either to the left or to the right depending if the key value comparison is less or greater than the key. So for example, if we will look for 161 as our key, we need to start from the root and then we compare that key to the root node. So, since 161 is greater than 137, we traverse dun sa right side ng tree. Okay? So, for 271 naman, since 161 is less than 271, then we look at the left. Okay. So, since nakita na si 161, if this is a dictionary implementation, then this has the link to the data or the value when we search an element. Mm, However, if we are searching for an element that is not in the BST, we also need to do the same method, but it will end up saying na hindi nag-e-exist yung element doon. We need to identify whether that element is in or not in the tree. So for example, let's look at 320. So if we check, given this current binary search tree, if 320 is here or not, what we can do is to do the same operation. So let's try to compare 137 with 320. Since 320 is greater than 137, look at the right subtree. Since 320 is greater than 271, we look at the right subtree ulit. Since 320 is greater than 314 at wala nang nag-e-exist na right subtree sa 314, then we can say that 320 is not in the tree. So, yung number of comparison natin is less compared to checking all the elements in this array, or if it's in the array representation kasi we'll need to check all elements. But with the binary search tree representation, kaunti na lang yung number ng comparison that we need to do. Okay. So another operation is inserting an element into a binary search tree. But to do the insert, we need to search the proper position or the correct position of the key. Maintaining the property na dapat ay lahat ng nasa right is greater than the node and lahat ng nasa left is less than the node. So, for example, if we wanted to insert an element na 166 into the tree, we search for their location as if nag-exist siya doon sa tree. So, by traversing the tree from the root, we can compare again kung saan siya dapat ilagay. So, if 166 yung key natin, we know that dapat nasa right side of the tree siya. Since 166 is less than 271, then dapat nandito siya sa left subtree ni 271. Since 166 is greater than 161, dapat nasa right subtree siya. Lalagay natin si 166 sa right subtree ni 161. So that's for inserting. Okay? So yung deleting naman na operation is not that intuitive compared to searching and inserting. Kasi for deletion, madali lang siya if we are deleting a leaf. Pero ang question is, saan mo papamigay yung children ng particular node pag nagtanggal ka? So, for example, you can try to delete 60 from this tree. So, 60 is this one. So, it's a leaf. So, it's as simple as just removing this node. However, if yung node natin is 73, we need to identify kung saan pupunta yung subtree na na descendants pa ni 73 na delete natin, and making sure that the resulting tree will still be a BST. So, for example, if we remove, let's say, the root node, what will happen to the tree after deleting this? Hindi naman pwedeng maging two disjoint subtree si BST. So, we will be discussing the three cases for deleting an element given a BST. Okay, so suppose we wanted to delete 60. This is the first case and the simplest case because if the node has no children, you can just remove it. Okay? So, okay na tayo dyan. If we are removing a key na merong one child, okay, Ang mangyayari is remove it. So, we can remove this 73 and replace it with its child. So, si 42 na dating anak ni 73 ay umalit dun sa pwesto ni 73. Okay? Okay, that's fairly easy for case 1. However, what about if mag-e-exist yung left and right child ng particular node na dinidelete natin? Basically, it will disconnect the tree if you delete this one. But how can we create one binary search tree from this deletion? So if we remove 137, what will happen is that we need to follow certain processes. Okay? What we need to do is first, mm, replace that node with the um, successor of the deleted node in the in-order traversal. So, kumbaga, sino ba yung kasunod ni 137? In this case, if we have an in-order traversal of this tree, meron tayong 42, 137, left, 161, 166, 271, 314. So, yung successor ni 137 is actually 161. Since 161 yung next, what we need to do is, first step, replace yung dinelete natin na key, location ng dinelete natin na key with the successor, and then we delete this key. Okay. So, since deletion of this key will use yung case 1 natin kanina, what we will do is to remove this one and replace it by its only child. So, ito ay magiging 166, just like what happened here. Okay? So, just to summarize, case 2 is when we have two children. What we need to do is to find its in-order successor, which has 0 or 1 child, replace the node key with its successor key, and then deletes its successor. Given those basic operations na search, insertion, and deletion, we know that the basic operation necessary for those is key comparison. And the key comparison is bounded above by the height of the tree. So the time complexity of all the operations, insert, delete, and search, is dependent on the height of the tree, which is the longest path that we can take. So for the best case, we have log n. And that is kapag compact yung tree natin. However, in the worst case, our height of the tree is theta of n, and some operations will take linear time, so wala na tayong pinag-iba sa array implementation. Pwedeng mangyari itong theta of n if we have a left-leaning tree or a right-leaning tree. It's still a binary search tree kahit non-linear na um, yung, yung itsura niya, because we can still say that the property is true for right-leaning and left-leaning tree. So the challenge for binary search tree is how to keep it balanced. So how to minimize the height of the tree. So yung mga di-discuss natin later on, like red-black trees, EVL na na-discuss na natin before, ang goal nila is to minimize the height of the tree or to make it more balanced.